Hello, this is Jennifer Tassinger with A Plus College Ready, and I'm here with you today to go over LeChatelier's principle. So LeChatelier is the principle where if a stress is applied to a system at equilibrium, the position of the equilibrium will shift in the direction to reduce that stress. So the direction is influenced by concentration, pressure, and temperature. So if you notice to the right over here, this great chart that I have, the first two rows are talking about concentration, if I increase them or decrease them. The second two rows are if I increase pressure or decrease pressure. And I want to point out, if I increase pressure, the shift will occur towards the fewer moles. So think your balanced reaction. Think the volume, of course, is going to decrease, the pressure is going to increase. If I decrease pressure, well, obviously volume is going to increase, and I'm going to shift towards the side with more moles of gas. Notice temperature. Heat it up, speed it up. It's going to heat. If the temperature is increased, it's going to go away from the heat or energy. So exothermic reaction is favored, of course. And then if I decrease the temperature, it's going to move towards the heat. Most of the heat energy will need to be used produced for that loss. So it's going to shift away from where the heat is being added or decreased in this case. The last part of this chart is if you add a catalyst, there's no shift because basically a catalyst just speeds things up. So we're going to talk about how the system will relieve the stress in terms of magnitude of K. So remember K from equilibrium basics. If K is greater than 1, then the equilibrium is shifting in the product side. In other words, there are more products being formed than reactants. If K is less than 1, then the formation of reactants is favored more so than products. If you notice my example to the right, we're using LeChatelier's principle in terms of the Haber process, and the Haber process is just making ammonia. If you notice in the first two rows, if I add more nitrogen or hydrogen, again, those reactants, I'm going to shift the equilibrium to the right, to the product side. So again, K would be greater than 1. If I add more ammonia or remove ammonia, then I'm going to shift the equilibrium to the left, therefore K would be less than 1 because it would be the reactant favored side. And again, adding a catalyst, no effect on K because it'll just speed up the rate of the forward and the rate of the reverse by lowering what's called the activation energy. Remember we looked at that at thermochemistry? The hump on the graph. Excuse me. So what happens when we're not at equilibrium? Well, when you're not at equilibrium, or you're said to be at initial conditions before equilibrium is established, you have this thing called reaction quotient. Notice again, you're going to have a balanced chemical reaction. You're going to use the law of mass action, but this time you're going to write it for Q. It's the same exact way for K in terms of the products are raised to their coefficients over the reactants on the denominator side, raised to their coefficients. So Q has the appearance of K, but remember, the conditions are not at equilibrium. Watch those key wording. So when Q is less than K, the system's not at equilibrium. The reactants are shifting toward the product side. When Q is equal to K, of course, we have equilibrium. When Q is greater than K, that means the system's not at equilibrium, and we're going to have to shift from the product side back to the reactants. So let's talk about the K to Q. Well, this slide right here is dedicated to if you have issues with Q to K, K to Q, what to do, which one to write. Here's a trick. You put them in alphabetical order, K, then Q. The greater than, less than sign actually will point the way for you. So if you put K is less than Q, notice the arrow is shifting towards the reactant side. Notice when K is greater than Q, the arrow is pointing towards the product side, and the product side is favored. So that's just a little trick. But be careful, multiple choice questions are really written in terms of Q to K. So you're going to have to do some flipping around to make it easier for yourself. So here's that graph again with the Haber process of forming ammonia. And notice the initial equilibrium. This is what we're talking about in terms of hydrogen is at a concentration of 3, so it will be at the highest part of the graph. Ammonia has concentration of 2, because we're going to assume the coefficient of 2 is 2 moles per 1 liter, which would be concentration of 2, molarity. And then nitrogen. When nitrogen has a 1 molar concentration and is added, notice this gigantic peak. But then as equilibrium is established, the hydrogen will still be above the ammonia, and the ammonia will still be above the nitrogen based upon those coefficient concentration reactants and products. Tongue twister. So if you change concentration but hold pressure and temperature constant, the stress will shift to alleviate the condition. So if I increase the reactant, I'm going to shift to the product. If I increase the product, it's going to shift to the reactant. Now, a little note to yourself. If a product is insoluble and falls out, then the right side will favor. Now, why? Because it's going to run to completion because all of the reactant is going to be used up. So we're going to be looking at slightly soluble or, quote, insoluble salts. We like to say slightly. In terms of once they're put in a reaction in solution, they're pretty much going to be used up and stay to the product side. Let's look at some example problems. So notice that I have here the PCl5 plus chlorine is going to yield PCl5. Oh, PCl3 plus chlorine is yield PCl5, excuse me. Again, notice reaches equilibrium. So we're not at equilibrium. And I put my products over my reactants. And I notice that my Q value is going to be less than K when what happens? Well, if I add chlorine, it's going to shift, right? If I add more PCl5, I've added more product, therefore it's going to shift to the reactant side. Q will be less than K. Or Q will be greater than K. So pressure. Again, third verse. When you increase pressure, you're going to go to the side that favors the least amount of moles. So the number of moles of gas is crucial. They're not going to be equal to each other. So you got to pay attention to your coefficients. And equilibrium favors the side with the least number of moles. So if there are more moles in reactants, the shift is naturally going to go towards the product side. If there are more moles of products, the shift is going to be naturally to the left or reactant side. Remember, mole ratio is huge. So here's an example. Notice the combined mole amount of my reactants is 2, and therefore my moles of my product is 1. So when I'm looking at this, I'm going to shift naturally to the product side. Now, what happens when the volume is halved or when the concentration doubles? Look at the denominator of Q. The numerator is the products and the denominator is the reactants. So if I change it, double it, triple it, it's going to affect the shift in which direction, depending upon if I'm looking at my product side or my reactant side. If you add a gas that's, quote, inert or not a reactant or product, it's not going to increase the partial pressure of those gases. So it will not affect K. It'll increase the overall pressure, but it will not affect K. So be careful when they say that they're going to add like argon gas. Not going to affect K. If you change temperature, this is where we have to look at the thermodynamic value of the reaction. So if the reaction is exothermic, the opposite will reverse. So if you add heat, the stress favors the endothermic reaction. Remember, endo absorbs heat. Endo is also going to be on the reactant side. If you remove heat, the stress favors an exothermic reaction. Remember, heat would be, quote, written as a product. So watch the changing of heat, like adding or removing. So think as heat in terms of a reactant or a product. Which way is it going to shift away from? So here's some examples. They'll give you a delta H positive value. Of course, that's our endothermic. And then they'll give you an exothermic reaction, a negative delta H. And so when you add heat to an exothermic reaction, it's going to decrease K. Why? Which way is it going to shift? It's going to shift towards, you got it, the reactant side. If I add heat to an endothermic reaction, it's going to, of course, cause the reaction to go towards the product side and increase K. And remember, one more time, catalyst, no effect on K. So there you have it, all things LeChatelier's principle. If you have any questions or any problems at this time, refer back to each slide. Look at that chart that was on the second slide. It really is a great summary. And practice, practice, practice. Take the time to start practicing those practice problems and getting an understanding of these three categories of LeChatelier's. Until next time, good luck with all things equilibrium.